We throw around the word power all the time, right? We talk about powerful people, powerful cars, powerful ideas. But in the world of physics, power has a very specific, and I think, a much cooler meaning. It's not just about what you can do. It's all about how fast you can do it. So let's break that down.
To really get to the heart of this, let's start with a question. Picture two weightlifters. They are lifting the exact same heavy weight. One of them just blasts through the reps, super fast. The other one, well, they take their sweet time. So who is more powerful in the eyes of physics? Keep that question in your head. By the end of this, you'll know the answer for sure, and exactly why.
Okay, so before we can really truly understand power, we gotta start with its essential ingredient, a concept called work.
In physics, work is actually incredibly simple. It's just the act of using a force to move something a certain distance. That's it. Did you push a box across the room? You did work. Lifted a book onto a shelf? Yep, that's work too. But here's the crucial part. Work doesn't care about time, not one bit. It only cares that the job got done.
And this is where power storms onto the scene. If work is the what, the task itself, then power is the how fast. It's the rate, the speed at which you get that work done. It's all about how quickly you're using or transferring energy. When we talk about power, time is literally everything. And it all boils down to this one simple, elegant little formula. Power equals the work you did divided by the time it took you to do it. This little ratio is the key to this whole thing. Do more work in the same amount of time? That's more power. Do the same work but in less time? Well, that also means more power.
Okay, so to make this distinction crystal clear, let's put work and power head to head.
So here's the bottom line. Work measures the total accomplishment. You lifted the weight, you climbed the stairs, job done. It doesn't own a stopwatch. Power, on the other hand, is completely obsessed with its watch. It's always asking, how fast did you do that? How quick was it?
So, how do we measure this stuff? Well, the standard unit for power is the watt, named after James Watt. And 1 watt is super simple. It's just 1 joule of work being done every single second. Now, you've probably also heard of horsepower, which we still use for things like car engines. Just know that 1 horsepower is a lot more powerful than 1 watt. We're talking about 750 times more.
All right, enough with the definitions. Let's apply this to a couple of real-world scenarios and see if you can spot who's really packing the most power.
Okay, here's our first showdown. We've got Will and Ben. They are both lifting the exact same barbell the exact same number of times. The only difference is that Will takes a full minute to do it, while Ben just flies through the set in only 10 seconds. So who is delivering more power?
And the winner is Ben, by a landslide. I mean, it's not even close. Think about it. They both did the exact same amount of work. But because Ben did that work 6 times faster, he was generating 6 times more power.
Okay, let's try a trickier one. Jack and Jill are running up a hill. Now, Jack is twice as big as Jill, so he has to do a lot more work to lift his body up that hill. But Jill is way faster. She gets to the top in half the time it takes Jack. So who's more powerful now?
And surprise, it's a tie. They are equally powerful. How can that be? Well, just look at the ratios. Jack does twice the amount of work, sure, but he also takes twice as long to do it. Jill does half the work, but she does it in half the time. So when you divide the work by the time for each of them, the ratios end up being exactly the same. They cancel each other out perfectly.
So we've seen the idea in action. Now let's get our hands dirty and plug some actual numbers into our formula.
First up, we have a very tired squirrel. This little guy does half a joule of work, maybe he's lifting a tiny acorn, and it takes him 2 full seconds. So, what's his power output?
We just follow the steps. It's pretty simple. We know the work is 0.50 joules. We know the time is 2.0 seconds. We just grab our formula, P equals W over T, and plug in the numbers. That's just 0.50 joules divided by 2.0 seconds.
And that gives us a power output of 0.25 watts. Not exactly a powerhouse, our little squirrel, but hey, he got the work done.
Let's try one more, this time with a student doing a chin-up. She has a mass of 42 kilograms, she lifts her body 1/4 of a meter, and does the whole thing in 2 seconds. What's her power?
Okay, this one has an extra step. First, we gotta calculate the work she did. And work is force times distance. So we figure out her weight to get the force, and that gives us about 103 joules of work. Okay, now we can use our power formula. We divide that work by the time, 2 seconds,
And we find out that the student delivered 51.5 watts of power. That is over 200 times more powerful than our tired squirrel.
So after all these examples and calculations, what's the one big idea that you should really walk away with?
It really all comes down to this. In physics, and maybe in a lot of other things too, real power isn't just about the size of the job. It's about the speed you can get it done.
And I'll just leave you with one last thing to chew on. Think about a huge semi-truck. It's doing an incredible amount of work, hauling a super heavy load slowly up a long hill. Then, think about a lightweight race car. It's doing less total work, but it's accelerating from 0 to 200 miles an hour in just a few seconds. Now that you understand the physics of power, which one do you think is actually the powerhouse?